into number of intervals. Let me take 0 to 5. Okay, let me take 0 to 5. This is sin x upon x, the first integral, plus if I take pi to 2 pi, no problem, this sin x upon x dx plus and so on. Okay, and last will be we take r minus 1 into pi to n pi, or r into pi. Let me take, here it is r into pi. It is sin x upon x here into dx. Okay, so this is what you call. Now in this situation, the first function is convergent here. While limit x tends to 0, you know that sin x upon x this is equal to 1. Since, let me say, since here, since you know limit x tends to 0, sin x upon x is equal to 1. This is by definite integral. Or if I take it by L'Hospital's rule, suppose, because 0.0 is still in non-determined form or undetermined form. Okay, if I differentiate numerator, it is cos x, the denominator is 1, so cos x when x tends to 0 it is 1. It is 1 in that situation also. And by limits of functions and limits we have discussed about, or we discussed about, that in the beginning of integration and differentiation, limits and continuity, in those limits, limit x tends to 0, sin x upon x is 1. This we always know. But even if we apply the L'Hospital's rule, in that situation numerator and denominator is 0.0 form, but at x equal 0 to 0.0 form. If I apply L'Hospital's rule, differentiating numerator and denominator separately, then applying the limit again, it is sin x differentiation is cos x divided by 1, because x differentiation is 1, so cos x upon 1 is cos x. If I put x equal to 0, cos 0 is 1, so this is 1. In this case, the first is, it is convergent. First part is convergent. So, first part is convergent. It's convergent. Okay, now if I take the last part, or at x tends to infinity, let me take. Okay. At cos infinity, it will be 0 in that situation. If I take mu more than 1 or something, so that in that situation it will be. And if I take that limit x tends to infinity, the last one. Okay, and this is sin x upon x. And if I take x square here, no problem. Okay, so then in that situation it will be, if I take x to the power half, then the denominator will come out as x to the power half here. Let me take x to the power half. As I just discussed about in the previous question, 15th one, I put the 3 by 2 power, that by 2 power, it will come in the denominator. Then apply x tends to infinity. In the denominator it will be x infinity, because infinity is 1.0, it will be 0 in that. It is 0. So here, a is equal to 0 and mu is equal to half. It is convergent. Okay. So it is convergent. Okay, in the when a is 0 and mu is 1.2. But if I take in between pi to 2 pi, 3 pi, at one of the points here was sin pi is 0. Again, this is pi, so 0 point something is 0. In that situation, even if we are not taking mu any number, mu less than 0, or mu may be greater than 1, so this is x into this, so 0 into 3 is 0. Everything will be 0. The limit is comes out to be 0. In that situation, if I take modulus of this value, okay, and if I take 0 to, let me take infinity, is absolute value of sin x upon x, where separately I take it. In that situation, this value will be, but sin x is absolute value, but even that it's 0 here. In that situation, it will come out to be 0. And if I take mu greater than this, mu less than 1, and even if I take mu greater than 1, in that situation the limit will be this one proper one. I mean, because limit is finite here, because 0, so this is proper integral. Okay, the first part is proper integral. In that situation, the function is converges or is convergent even if a is equal to 0. But mu we have taken, even if, let me take here, even if we take mu greater or equal to 1 positive and a equal to 0, that means limits in that situation will be 0, that means it will exist, and even then the function will be, the function or the integral will be, okay, what you call integrable, or it is finite here, then the function will be convergent. Okay, so a is 0, mu is less than 1 or greater than 1, even then the function is convergent. Why it's not absolute? Because in case of infinity, if I take, then it is equal to infinity in that situation, final situation, when n is not defined, sorry, n tends to infinity. Suppose n tends to infinity, if I take the last one, this is r minus 1 into pi to n pi, let me take. Here limit n tends to infinity. Here n tends to infinity here. And this is sin x upon, if we take absolute value of sin x upon x here. Okay, so in that situation, n tends to infinity. If I take sin n pi, so this is infinity, r minus 1 to pi to infinity here. In that situation, the function, this will be 0 here, because this axis, if I differentiate sin x, is cos x, cos 0 upon cos x upon 1. In that situation, if I put n tends to infinity, and cos infinity is not defined, or is, if I differentiate that, in that situation it will be cos, let me take cos x or cos alpha. If I take separately, cos alpha minus cos x, the greater or equal to 2. If I take separately, integration of, this is 0 to infinity, if I take, this is sin x only. It will give us cos alpha minus cos, this is a to, let me take a here, any number in between 0 to a to infinity, so r taken a to infinity, one of the limits here. So it will give us cos alpha minus cos x. In that situation, the value is greater or equal to 2. It is finite value. In that situation, it is finite value in that, okay, because cos alpha minus cos is greater or equal to 2. And then, in that situation, it comes out to be finite. So this value is not absolutely convergent, because sometimes it comes out to be 0, and mu is greater than 1 or less than 1, doesn't matter, but it is 0 sometimes, finite value, and in this situation, if I take numerator only, then value comes out to be more than 2 after integration. If the integration of sin x is minus cos x, then minus plus here, it will be cos alpha, lower limit. Cos alpha minus cos x, which is greater or equal to 2, if I put the limits here. This value comes out to be positive. It means it is convergent here, but not absolutely, because in the end point, sometimes it is 0, okay, and sometimes finite value comes out to be as 1. The first part was 1, and second part was 0, a equal to 0. So not absolutely convergent, but it is convergent. To prove that the integral 0 to infinity sin x upon x, yes, converges, but not absolutely. I mean, 1 or 2 point, 1 point finally at infinity, the function comes out to be 0 there, a equal to 0, or it may be infinite, not defined. Okay, so in that situation, we say that all these functions are. So this ends the topic of convergence of improper integrals. Improper integrals are talked about. First, I discussed about what are the improper and proper integrals. Then, comparative test. What is comparative test of improper integrals? First kind of improper integral, second kind of improper integrals, then third kind of improper integrals. Any improper integral which includes first kind of integrals properties, characteristics, and second kind of integrals characteristics. That means the limits are infinite, the margin to plus infinity, and the integral within and the integrand given is bounded in that situation. Okay, so that means the function is convergent. Okay, then the improper integral is convergent in that equation. That is improper integral. That improper integral, if it is bounded, or means integrand is bounded, in limits are infinite, then is the first kind of integral. If the limits are finite, 0 to a suppose, okay, and the function is not bounded, okay, that is unbounded, in that situation this is of second kind of integral. And if the integral given limits are infinite, function is not bounded, okay, that situation this is of third kind. These kind of improper integrals I discussed about. Then compared to test, quotient test, multiple testing, ABEL'S test, and DIRICHLET'S test. All kinds of tests I have discussed about. Comparison test, DIRICHLET'S test, quotient test, ABEL'S test, okay, mu test. All these tests I have discussed about. On the basis of these tests, we define that what are the convergent integrals, improper integrals, or what are the divergent improper integrals. Okay, divergent means when a infinity, the value of fx upon gx is infinite, comes out to be infinity. Okay, and the function then gx is diverges. That means the whole quotient will be divergent. So in that case, divergence and convergence we have discussed about. Okay, when the functions are convergent, when they are divergent. All this ends the topic of improper integrals. Now next I'll discuss about the areas. What are the area of a bounding figure? Okay, curve tracing of the curve, how to tracing of the curve is done. Then okay, then quadrilaterals we talk about what the area of quadrilaterals. So areas topic of area in integration we have left over. So that is the only last chapter, last topic I mean, that we will discuss in the next. Because number of questions students have asked me about volume or how to find out volume of it with the help of integral. Okay, solid volume of a solid figure, volume of a quadrilateral, volume of a four-sided figure, volume of a triangle, sorry, volume of a area of a triangle. So area, quadrilaterals. Okay, so that means we have to discuss about areas of quadrilaterals. Okay, that is curve tracing. We will talk about what is the singular points, curve tracing, etc. Multiple points. Okay, double points, multiple points, and we will talk about curve tracing, areas, volumes of figures. Okay, that is how solid figures, solid revolution of figures. That we will discuss in the next lecture series. Okay, then see you.